Hi, everybody. Thanks for coming to this presentation. And today I'm going to talk about this paper, which is a very interesting paper. And it combines two very hot areas of deep neural network research, which are adversarial training and interpretation of the DNNs. So what is the motivation of the paper? The paper looks at the different interpretability methods and tries to understand why the networks are fooled by adversarial examples. So what it does is that it looks at the original images, looks at the representation of those original images, and then does create adversarial examples and tries to understand why the mistake is happening there. And just quickly, what is interpretation? We know that we cannot understand why the deep neural networks are making some decisions. So the interpretation methods or algorithms are the ones that help humans to understand why the network is making a specific decision. And adversarial examples are some images in this case, or any data, that we have added some perturbation to the image or targeted noises to the image still to the humans, the images are very similar to the original one. We cannot differentiate them. But for the network, they are totally different things. So it's classified differently. So the idea here is to understand why this happens in the representation kind of area of the algorithm and mitigate that problem. So just to go to the key contributions, as I said, they look at the consistency of the representations. They found out that the representation between normal and adversarial images are not consistent. To measure this consistency, they come up with a new metric, which they call consistency metric. And then they suggest an adversarial training algorithm to mitigate this representation kind of problem that they have. And they show that it's the network which is trained with that method is improved. Yeah. Good point.
So are you going to later tell us about what it means for them not to be consistent?
Here.
Okay.
Yes. So what's happening here is that on the top, we have real images, which are classified by the network. And they are for different neurons, which are shown by the captions. So for example, if we look at the neuron number 147, which is one neuron in the network, we can see that when we have images which are classified as bird, that neuron is looking at the head of the bird. But when they have adversarial images which are classified as bird, and they look at the same neuron, the activation is happening randomly. It's looking in random places which are irrelevant to the head of the bird. So they call this inconsistency. They say, OK, before we thought that the network is looking at some semantic meaning. Now, because of these adversarial examples, we see, OK, there's this inconsistency. And it's looking on some patches, meaningless patches. And maybe it's learning that because it has looked at all these patches again and again and learned how to classify them. But when the example is irregular, it's fooled. Yeah, sure.
Did we have the assumption that they should be consistent? Why should we have such an assumption?
If they are consistent, so there are two hypotheses that why the network makes mistakes by adversarial example. One is that they look at the same things, but maybe because of those noises, the power of making a decision is reduced. So for example, here, they both look at a head, but maybe the power is reduced by the noise or something. The other thing is that they look at totally different things. So basically, if the network makes correct decision for the adversarial, we hope that it's looking in the same region at least. Like, because if the final decision is the result of all these activations of different neurons. So if we want to come up with a true decision, the activations should be similar.
So my intuitional understanding is that We have trained two brains, and we want to see that, okay, these two brains will, when they look at the same thing, the same neuron will activate. Is that the whole idea?
Yes, exactly.
Okay, thank you.
So is it also the idea of like a fraud detection problem, right?
Kind of. I cannot say it's like a detection problem here, but one problem in fraud is that you can fool the network, come up with like data which looks very original, but it's fraudulent.
Okay, I'm going to call that out. It's a
yeah, exactly.
It's a comparative question, so let's
just remember that. Yeah.
Let's ask clarification.
And for the network, is there some other nuance check the head of the bird for the adversary example?
No.
No, all the nuance just talk about.
Yes.
Okay.
I'm sorry, this might be a really dumb question, but I just want to make sure I understand all these pictures.
Sure.
So on the far left, where it says real images, those are all birds, and that means that neuron 147 in VGG16 conv3 layer has the highest activation for all those real images. Then for the adversarial images, the same neuron for those images, which are definitely not birds, is the one with the highest activation. Okay, and same with it. So, like, is that, like, why pick that one layer, for example? Like, why is it significant that that one neuron has the highest? Like, why not look at, like, the distribution? Like, so, like, so if I'm looking at, like, the mode, okay, so 147 is the neuron with the highest activation for bird. How do I know that it's only that one neuron with the highest activation that matters? Why don't I need to look at the highest, like the bottom quartile, top quartile? Like, why don't I need to, why is one
you mean
good enough?
why you are looking at only the highest activation? Why not like the second highest one?
Yeah.
So I don't have any. Do you want to comment on that?
I guess it's speaking to the interpretability of it. You want the high-level neurons to be able to, when you're justifying a decision that it was made, you want it to be able to say that this neuron is looking at this specific feature, which is not present in the adversarial examples, right? So you can see that if you were to try to say what does this neuron actually look for, you couldn't. I mean, I'm sure you could come up with some weird statistics or averaging of modes, but like this neuron is not an interpretable neuron on those adversarial images, right? So it's saying it's not robust.
I have a question. So say it is a fourth in the first line, the corresponding adversarial is on adversarial images the fourth in the first line, right? Mm-hmm. And so then you would expect to on the adversarial image, at least on the same region match, right? The feature you're looking for.
I don't think the region is very, like the concept is more right. Like the semantic meaning, like it's at least the head, it should be the head of the bird, for example. If by region you mean like the placement, I don't think that's that. It's like the concept that it's looking at.
Right. Quick question. So the adversarial architecture and the normal classifier architecture are the same, exactly the same? The discriminator part of the adversarial versus the classifier.
I will talk about it. They are different in this case, but in the training part, they are the same.
Oh, so they are the same.
Yeah. But in this example, they are different.
So if they are different, they should be consistent, you know? If they are the same,
if the network is highly robustly is trained, we hope that there is no adversarial examples for that network. So that's the goal, to come up with a network which cannot be fooled. That's the idea of adversarial training.
So I understand, but somehow I got confused. The point is that we have made a discriminator which we hope that will act the same way as our classifier does, because the classifier
here we don't have any discrimination.
This is not GAN.
Yeah, this is not GAN. So the idea is, so the concept of adversarial here is just we have this original image which is classified, for example, as cat. Right. And then we perturb it a little bit in a way that is classified as dog, for example. which shows that the networks are not like that robust to these classifications, which is not good. And we want networks which are trustable. They are not that sensitive to the noises.
So you want to say that they are more resilient to noises. That's the whole idea.
Yes.
Okay. Thank you.
Yeah, sorry. I'm just wondering, for example D, is there a reason why there is like one real image and one image that's replicated in the adversarial image, like the image of the pug, I think, in the top left example?
So the idea is that these adversarial images are not from the same class. So there has been something like a cat, and then they targeted it to be like classified wrongly, and that one came up to be a dog, and that neuron is working good in that case. Yeah, so that's what we are expecting to happen for all the cases, but for this one, it's working.
So those red squares mean that, oh, it made a mistake.
Exactly. Thank you for that.
Can you talk about how to generate the adversary examples?
I have lots of slides.
Okay. I just want to make sure normal and the adversary picture share the same patterns.
All right, let's carry on.
Let me move on.
Future slides, you have a question?
Sure. So this paper doesn't talk that much about like details, so I decided to add a few slides about each of the details that are included in the paper. They help us in the discussion part, so I try to be as fast as possible because I'm sure lots of you know better than me what these concepts mean. So I start with interpretability, and then a little bit about adversarial attacks, and then a general idea what adversarial training is. And then I get back to the paper talking about the consistency metric, the method they proposed, and finally the discussion points and results. So for interpretation, there are like generally three different ways. It's like forward passing, gradient backpropagation, and black box, which are based on perturbation. And this paper uses a method which is like from the third group. So why we say DNNs are not interpretable? If you look at the weights that we learned from the image in a classifier, we see something like this. So these are the kernels in the CNN. In the first layers, it's easy to say, okay, this one is like edge detector in different angles, but when we go deeper, it's impossible to say what that neuron is looking at. So we want to come up with an explainable region in the image. In the first paper, kind of the first series of the paper, which were published by in Hinton's group, they looked at the latest feature space and tried to find out what are the closest feature space images. And what they found is that if you look at left, that's a very simple nearest neighbor classifier, which usually looks at the pixel values, the background, and comes up with decisions based on those pixel values. But in DNNs, when we look at the feature space, we can see that they are looking at concepts. The backgrounds are different. The colors are, in some cases, very different, especially for the dogs. But they still are looking at the concept. They found out the concept from the image, which motivated for the next kind of explainability like papers. One of the very good first tries was this paper, which they looked at the activation. It makes sense for us to look at that now, but in those age, it wasn't. And they found out that some activations, for example, that one which is shown by the green box, is looking at the face. And this classifier was a face detection. So they found out that there are neurons which look at something semantically meaningful. Of course, knowing this, the next meaningful step is to just feed the network with a bunch of images and see which patches in those images activate each neuron highly. So each neuron, what is the highest activation value of each neuron for each patch of the images? So you can see that, for example, on the image, some neurons are activated by circular patterns like eyes, wheels, or with faces. So again, they found out that networks find some meaningful concepts in the image. The second group, which are looking at the gradients, started into kind of with this paper. So what they do is very similar to training. So in training, what we do is that we feed the network with something. We look at the output and find the gradient of the loss function or the output regarding to the input. And we backpropagate that gradient. Here, that's a very similar concept. If you look at the top one, you can see the gradient that the network is trained with. But if we fix the weight and then look at the gradients and just keep the positive ones, we come up with something like the bottom one, which is called the guided backpropagation. And you can see that we find some meaningful concepts there. Now, this is a cat classifier because it's looking at the face of the cat, like the eyes of the cat. And why we look at the positive side only? Because we want to find out the positive effective, like the positive feedbacks that the pixels which are giving positive feedbacks to the network. We don't want to see which one are demotivating a class. So we just keep the positive ones.
So just a quick clarification comment perhaps. So when you say we're visualizing gradients, you're saying that if they're receiving higher amount of, if those pixels are receiving higher amount of gradients, positive gradients, then we highlight them, we show them.
Exactly. And like the last one was looking at the gradient of the output regarding input. We can look at different gradients as well. For example, in this example, which is one of the well-known algorithm for interpretability, they look at the feature map right before the softmax and find the gradient in respect to the activations of the final convolutional layer. So you find a gradient, find the average, and then multiply that average of the gradient by the activation map. You come up with weights. Again, you filter it with only keeping the positive side, and you come up with that heat map there, which shows the region that are mostly affecting the decision.
So I know you want to move fast, but could you quickly repeat that?
Of course. So Y over there is the like the output of classification, but we look at the features like the layers before the softmax. So we have that as the output, and we find the gradient of that in respect to A, which is the activation of the final convolutional layer. So we have let's say gradient of Y over gradient of A, and then we find the average for each channel, and then multiply that average 2 times that A. So what it does is that actually it's looking at the weighted summation of the activations of each channel, which shows that, okay, my output is sensitive to this channel this much. And then when again, you keep the positive side because we're interested in the positive side, and do an upsampling to make it the same size as your input. It comes out with this heat map. The third group are perturbations. They are very simple. What you do is that you remove some parts of the image, look at the output, or just or you may replace them by random patches and look at the output. If they are important, the output of the classifier drops a lot. If they are not important, that won't change the output. So doing this perturbation, you can come up with heat map, say, okay, this part is important, that part is not important, and come up with it. And that's the method used in this paper for interpretability.
What was RF?
Random.
Fields?
No, I forgot that. It's like this way, the numbers between 0 and 1 is called RF. I forgot.
Receptive field?
Yeah, receptive.
Okay, okay. That makes sense.
Yeah. This is the thing I want you to remember for the discussion points. These are like the outputs of different methods, and this is from that GradCamp paper. Although they kind of are similar, they're looking at similar concepts, they are not 100% the same. So it means that if we use different interpretation methods, the heat map or the place that the network comes, the method comes up with are not 100% the same. So, which means that the interpretation methods are not 100% consistent as well. Adversarial attacks, two ways, white box.
Sorry, if you go back to the previous slide.
Sure.
What are you comparing with what?
I'm just looking at the heat maps that the different methods found out. Like you can see that guided backpropagation for cat is looking at the dog as well. But when you filter it with GradCam, it's just looking at the cat. It's just, or the area that ResNet is looking at is different from the area that the VGG is looking at. Exactly. So I want to say that the interpretation is algorithm dependent as well. So adversarial attacks are like two ways. White box, when you know everything about the network, you have access to the network, you can calculate the gradients. Or again, there are black box, which you don't know what is going on inside the network. You have only access to the input and output. What we do, we want to solve this problem. We want to find some perturbations which are as small as possible, hopefully not detectable by humans. And we want that small perturbation change the class of the image. So if the class of X, which is the image, is not the same as class of X plus R, which is the perturbed image. If we assume everything is linear, it's a linear classifier, we have this linear boundary. We can find the distance between the image X0 to the boundary and then move it to the other side of the boundary. So we find the smallest path, move it to the other side. That's the simplest thing we can do. It's impossible because the networks are not linear, but it's a good assumption to start with. And DeepFool, which is one of the good methods, does that.
Okay, sorry for interrupting. I just want to make sure it's clear. So you have a delta X K hat?
Yeah, so that delta is the optimum perturbation.
Okay.
You want, yeah.
So you want to optimize for that. And then
you want to optimize for R, and then the final thing is like that delta.
Right.
So you might.
So you want that to be the minimum. You want that delta to be the minimum, right? That's.
Yes,
okay,
exactly.
Yes. And then what was R again?
R is noise, like perturbation that you generate.
And when you say subject to K of X plus R.
And K is the classification label.
Right, you want it to be not equal to K. Okay, gotcha.
So, for example, if we find a delta and we reverse it, so how we are sure that okay, it's not possible for humans to understand that there has been a noise because
sorry, I didn't get the question.
Because the assumption was that we want to change the class of the data by moving it minimally, and also it's not detectable for a human being as much as possible.
We hope that if that perturbation is very small, it's not detectable by humans.
We cannot guarantee.
Right? But it cannot be guaranteed. And in many cases, you can see the noise, or you can see that the background is changed. Especially when you have, for example, MNIST, which is black and white. You can see that it's adding some grayscale things to it.
Yeah.
So
Let's
yes.
skip that for the discussion. That's argumentative, right?
Yeah. One of the mostly cited papers, or maybe like the first even like paper, is the ones from Goodfellow's paper, and it's called fast gradient sign method. So what it does is that it wants to maximize the loss function. So we want to minimize that perturbation. At the same time, we want to maximize the classification error. Hopefully, it goes to the other side. It's very fast, and sometimes that's the case. It's detectable, but still, in this example, it's not detectable that much. Again, this one relies on linearity of the network as well. which is not the case in reality. And in this paper, which is a very nice paper.
Sorry, with respect to X or weights? Linearity. With respect to input or the weights?
It just uses one gradient, so it's like in respect to the loss versus loss is kind of the loss should be linear so that we have like one gradient works like in maximizing the output. Yeah. Sure.
I'm just thinking of like the way this picture is being tweaked and being back propagated back from the labels, like the method of introducing the noise.
Which one?
Just the whole method of
Oh.
how you drive that noise.
Mm-hmm.
What if you were to change your method of choosing the label? Like, what if you made some requirement whereby, okay, if I'm going to tell the difference between like a macaw and a bookcase, if I choose the label macaw, like my neural network must be like 10% more confident that it's a macaw than any other label. Like, what if I put some like confidence like bound there so that it can't choose that unless it's more, because this like little change here implies that when I take, say, something like argmax of my final labels, like two of the labels are really
very
close.
simple to do when you have a binary classifier. But like in ImageNet, you have like thousands of classes to be classified. It's like, can't I just require? Have you looked at like the differences between classes when you have like hundreds of classes? Maybe they are like 0.1%.
But can't I just like require that of all of those classes, it's my probability, quote, probability distribution, which is really confidence distribution, has to be almost more and more like a delta function on that one. Because if I have like a million, right, I just add up, 999,999, and I require
that. If you impose that constraint, what happens is that the accuracy of your network drops a lot. So yes, it's more resistant to the noise, but it's not a good classifier anymore.
If you're pushing your decision boundary farther and farther away, then more images can fall within your decision bounds. So you'll get a higher misclassification rate. Right.
So would it necessarily have to be misclassified, or would I just say I don't know or something?
There are
so
techniques.
All it says is just classes, right? So if you're including more things in this class, you're going to misclassify. If that's
So this paper shows that all these assumptions about linearity is not true, and actually it works. It's the other way. Sometimes the adversarial examples that you create is not actually an adversarial example. For example, here 0, 0 is the image we start with. Epsilon 1 direction is the direction that is the adversarial direction you found, and epsilon 2 direction is the ones which is orthogonal to that adversarial direction. So what we are solving in FGSM is to maximize the loss, and the Z, or like the vertical axis is the loss value. So since epsilon 1 direction is the adversarial direction, we hope that if we move along epsilon 1, the loss function increases, like it gets maximum. But what is happening here is that in epsilon 2 direction, we get the highest thing, which is orthogonal to the gradient. And why is that? It's because if you look at the right image now, or sorry, left image now, you can see that the zoom, if we zoom into like around 0, we have these kind of non-local linearity, local non-linearities there, which shows that FGSM is not the best way of doing that, or that linearity assumption is not a correct assumption. And again, I want you to remember this because, again, in this paper, they use FGSM, which is not the best choice. We will talk about it.
Sorry, dumb questions. Yeah, can you just elaborate on this?
Yeah, so before repeating, do you mind also share, so if in this graph, if it's white, then is it closer to the optimum classification? And if it's blue, then it's further away. Is that correct?
Yes. So So the vertical axis is the loss. So the higher the value is, like the loss is higher. So it's like
So both color coding it and. So it's both. If you have that access, but you're as well.
Color coding.
Yes. Okay.
I think the color code is the same.
There is both the mesh, but the color indicates the value.
I see.
Somehow elaborate on it again, sorry.
Okay, sure. So what it says actually is that if you move along the adversarial direction, which is epsilon1 here, it's not always the best case. Sometimes other direction, in this case, even the orthogonal direction works better because it's maximizing the loss in the output.
What do you mean by best case?
I mean the best adversarial example. Because epsilon, like in the same value of epsilon1 and epsilon2, we have the same perturbation value amount. But if we move in orthogonal direction, we get a better, higher loss, which is a better chance of misclassification.
Does this guarantee that this should be misclassification in the orthogonal way?
No, there is no guarantee in any case.
How can it satisfy the constraint that you had in objective function?
So it's a completely nonlinear kind of optimization, and sometimes you cannot achieve the goal. Yeah, it happens. And I will just go through this very fast. The black box attacks are based on usually surrogate models. You have the input, you feed it, you find the output, and then you train a network on that input and output and try to attack that surrogate model. What adversarial training wants to do is the goal of adversarial training is to come up with a classifier that is not fooled easily with the adversarial examples. That's the goal. How we do that? So we minimize the loss function for even the worst, like the maximum loss function of H, which is like the worst adversarial case. So we want the classifier to classify the worst adversarial example correctly. It's very hard. Actually, it's a completely non-convex problem, so there are like methods to make it well-behaved. There are a bunch of papers. The simplest case to solve it is to just use FGSM to generate adversarials and then train the methods on those adversarial-generated images with FGSM. Again, this nice paper, ensemble adversarial training paper, shows us that the network, this training is easily fooled by coming up with very weak adversarial examples. So what happens is that instead of coming up with a network which is robust to the adversarial examples, it comes up with generating some like weak examples, which are easily classified. And that's how this thing is minimized. And they have suggestions to mitigate that.
Sorry, could you repeat the last point?
Sure. So we have a min-max problem. So what comes out of that min-max in reality, if you use that FGSM, is that the network won't be more robust. It's just that the adversarial example, it's trained in a way that the adversarials that you find are weaker than like the original network that could generate those like adversarials.
So it's still over-tuning to your adversarial examples as opposed to, in general, being robust to any.
Exactly.
So it's still limited to your data set.
Exactly.
So they just generate these adversarial examples. They just put them in the training set on top of the original stuff.
Exactly.
They train it.
Yeah.
Do they report any more robustness in terms of overfitting, or regularization effect of this?
Yes.
How more generalizable becomes your model when you do this?
Yeah, there is a nice paper by Wagner's, which talks about that. So they compare one of the big questions here is that even what norm should we use for that are L0, L2, L infinity, and what are the regularizations that could improve this. That Wagner paper talks about all these things. It's a very nice paper.
So it's sort of accurate to say, even if we don't achieve adversarial robustness, it's good to do this because it's
better
a way
than doing nothing
for avoiding overfitting and stuff.
Exactly. Yeah. So back to the paper.
Here's a question.
Sorry.
Yeah, so I'm just thinking, so is this also like an oversampling method just around the decision boundaries? And then so you can fine tune, make the decision boundary more, because like if you are in that embedding space, then you're just generating more around the cases there, and then you're making your decision boundary more continuous function around fine tuning, right?
Exactly.
Okay.
So that's the whole point, because like the easiest, and that's where like FGSM starts to find. The easiest way of fooling a network is to find out what samples are closest to the boundary and then move them to the other side. And and that's not the thing we want. We want even it works for the worst cases which are far away and could be misclassified.
Interpolation problem too, like the other day that the girl talked about, right?
Interpolation.
So we had a talk on this. Yeah. I encourage people to watch it, but let's not cover it right now. We can get back to this point in our discussion.
Can you just give your reference to which talk it is?
I don't remember the title.
It was something about VAEs, which are improved by interpolation. The space of VAEs was improved. Yes. So again, just to remind you of the problem, that's the problem. The network is inconsistent, and they want to solve the problem. And as I said, they come up with the definition of, they define it as being inconsistent. To be able to measure the inconsistency, they introduce this metric. It has two parts. One part is the consistency of each neuron for a concept, and that concept could be like a part of image, a concept in the image, texture, color, whatever you can think of as a concept. So it says, what if a neuron is activated by an image, what is the chance of, what is the probability of that image contains a specific concept, C. So remember this, and then they have another metric for calculating the correlation between the concepts, which are actually, this concept is the class labels. So let's say I have class which is defined by WI, which is the definition of that class, and then I have WJ. I look at the WordNet, which is shown on the left side. What WordNet does is that we have words, and then you can find the distance between the words by these three structures. For example, distance between Persian cat and dog is 3 because there are 3 connections between them. Or the distance between tabby cat and kitty cat is 2 because it's just only 2 edges between them.
What is tabby over here?
Sorry?
What is tabby over here? I know that B squares a distance metric, but what is tabby over here?
Could you repeat the question?
Sure. So he's asking what are these WI and WJ here. And I assume they are like the class labels.
Assume like word I and word J on the word bank graph.
Yeah, which in the network are the class labels.
Yes.
Yeah. So let's say I have a class of Persian cat and I have a class of dog. So I have word I as a Persian cat and I have word J as dog. And then I go to that graph there, which is from WordNet, and I can find a distance, which is defined by D here. So D is the distance in WordNet structure.
D is not computed by different vector, something like that.
No, it's just the distance between the words in that WordNet structure. Tree.
It's the graph distance.
Oh,
so WordNet is a manually constructed word relation graph.
So we hope to make the neural network the same way that we understand it. That's the idea.
Yeah, it does. And then, since we want to come up with that definition, depends on both N, which is the neuron, and C, which is the concept. We want to come up with a metric for a neuron. So we want it to just contain N. So what we do is to come up with, define this as a weighted covariance. So covariance of P, which is these probabilities for each neuron and all the concepts. A is a matrix which contains all these AIJs. And then we have this covariance matrix, PTAP, which tells us the consistency of each neuron. So this is the definition. P is, we can define the same, very similar concept for the adversarials as well.
Sorry, a dummy question again. So that P transpose AP, if it's higher, that means they're more consistent?
If it's higher, they're more consistent. Yeah. And then they come up with this suggestion for training. As you saw in previous slides, the regular adversarial training doesn't have the second term on left, which is the distance between the feature maps of the image. It just has this maximum of the classification loss. Here they added that second part and claim that adding that second part improves the consistency of the network. So here, L is the classification, the small l is the classification loss, and D is a distance, which here is the L2 distance. Phi's are feature representation, and here these are the last convolutional layers output. X star and X prime are two adversarial examples for that network.
So we are forcing the network to understand the environment the same way as we do, right? By saying that, okay, for example, these are the...
We are not forcing it, actually. That's only one metric, if it goes back. It's just a metric that compares like the outputs. But here, if you look at the learning, it has nothing to do with those consistency metrics. It's just they are telling that if we have this second term, which is purely based on the feature map, like the feature space, it becomes more consistent in this definition. So we are not actually forcing it.
So the D doesn't correspond to the WordNet anymore?
No, this D is L2 distance.
Oh,
so sorry, yeah, I know that paper is not. Yeah, so this D is different from that.
Oh, okay.
It's just L2 now.
Just to be on the same page, could you say once more what's the second term on the right is? So the first term is just the loss.
The loss function, yeah. Yes. So we want to find, and the second one is just the L2 distance between the feature map, and by feature map I mean the output of the last convolutional layer.
Feature map and so
between
which one
the
is
original image and adversarial image.
Gotcha.
So why did they claim that it could make it better?
Because the results show that.
So the adversarial is the perturb original image? Is that what it is?
Yes.
Okay.
Yeah.
Beautiful.
Yeah. In ideal case, that should be like an adversarial example that maximizes that distance. But since it's very hard to solve, they came up with this simpler definition. So they say, okay, it's hard to solve, so I get just FGSM examples. And if you see here, because we have two maximization, we need two examples for each training. We need X star and X prime as adversarial examples. It's hard to do both maximization and solve it, so they just say, okay, I keep them the same and calculate it with FGSM. And that's what they do. They have weighted summation of classification error for original image, classification error for the adversarial image, and the distance between the representation of actually feature map of the original image and the adversarial image. Yeah.
Okay, one last annoying one before you finish.
Sure.
So then we still have one loss function?
For both, yes. So that's the cross problem.
Right, so you have one cross-entropy loss function for both of them. So the difference is...
But it's calculated for both. So the value is different.
So
yeah.
are you then you're just minimizing it?
Exactly, exactly.
And
so we hope that because we want to adversarial examples to be classified correctly, so we want to minimize the loss for both image and adversarial. So we hope that doing this, the adversarial image is classified correctly as well.
Right. And what's the second? You're clipping?
That one is how they calculated X star. The clip is just to make it like a realistic image, which is between 0 and 255. And this is just a definition of FGSM. And what they did is that they ran FGSM multiple times, something between 10 to 20 times.
So that inside that clip function is FGSM?
Exactly. Yes.
Beautiful.
Sure.
Okay, a really embarrassing question, but that math symbol that goes squiggle D, what does that stand for?
Which one?
What is that operation? Expectation of X, Y, squiggle D. What's the squiggle D?
That one is just the data.
Sorry?
Data.
Oh,
Yeah.
Okay. Over the data set.
Yeah,
Okay.
exactly.
All right.
No, that's a good question. I like notation questions.
Yeah,
Okay.
I do. Yeah, so.
Beautiful. Let's thank the speaker and have a 5-minute break.
Thank you. So back to the paper and the results discussion part. So how they did the experiment is that they are using two image data sets, the ImageNet one and Broaden. So what they do is that they look at, they give all these images to the network and then look at each neuron and find the network, the images that highly activate like each neuron. For each neuron, they take around 500 images, and for each of those 500 images, they generate 10 adversarial images. And those adversarial images are generated by AlexNet, VGG, and ResNet. So in total, they have something around 500K adversarial images. To just summarize what I said, here for like on the right, you see that each of these dots is a neuron. They look at the activation of each neuron for each image. They choose like the top 1%, which is around roughly 500 image. They try to keep it like around 500. And then for each, they create 10 adversarial. So we have 500K adversarial images.
Sorry, are those neurons from the entire network or a specific layer?
I think they didn't mention it actually in the paper, but I assume it's for the entire. Yeah. I don't know actually. Since they have like this image, I assume it's like from all. I don't know. And they say 500, so there are like 1,000 neurons, so that cannot be the whole neuron.
Right.
You're right. So maybe like the last 100.
Right. Because if it's too early in the network, then it doesn't.
Nothing. Yeah.
Okay.
True. Okay. So just to show how the network is improved, the top image is the one that I showed it before, and the bottom one is after adversarial training. And you can see that now the neurons are looking at the same concept, dog face, like train wheels, whatever. So the network became like consistent. So that's the reason they say it's more consistent, because the results show that it's more consistent. And I think these images are cherry-picked. So this doesn't work for all the concepts. And actually, you can see what I said in these numbers. So on the right, they are looking at the consistency metrics. The top values are for the original, the regular kind of training. The bottom values are with adversarial training. And as you can see, the consistency, for example, for AlexNet, which is trained normally, drops from 16 to 11. Like I just removed the zeros. But with adversarial training, it's from 16 to 12. So it's not like a huge jump. It's just marginally an improvement, but it's an improvement. And it's the same for all other things. So it's improved. The consistency is improved. And for ResNet, they had the highest improvement. And that's the same for accuracy. That's another goal of adversarial training, to become more accurate even for the adversarial examples. So the top one is without the regular training. The bottom values are with adversarial training. And as you can see, again, if we compare real values to adversarial values, for example, the top one dropped from 54% to 4% for regular training, and it dropped from 43% to 17%. So it's improvement, which is, I think, an acceptable improvement. So for VGG from 68 to 8, now we have 62 to 25 for normal images. And for adversarial images, again, we have improvement as well. So it's more robust, but it's not like a huge improvement. And that's actually the case for almost all the adversarial trainings.
Sorry, the top was the top is the
normal training.
So why is it dropping? Is it not? You said it's so
we have real images and adversarial images. So for adversarials, the network is full, so the accuracy drops a lot. And for like to your point, she left. So never mind. Yeah. So as you can see, like top 5% is always more accurate than top 1. And this is just the histogram of consistent symmetric. The blue ones are the network which is normally trained. The left ones are the ones which are trained with adversarial training. And top is real images, bottom is adversarial images. And as you can see, the adversarial training improved the consistency. The histograms look very similar. While in the regular training, it's skewed to right.
What is the x-axis?
It's just a consistency value.
Before we go into that, we have a huge clarification question.
Sure.
If you can address that from online. Could you summarize how the authors make the connection between adversarial and interpretability concepts by intuition rather than the optimization equations? In other words, how the results and equations are in line with the title of the paper.
Okay, yeah. So they haven't done anything for actually interpretation, connecting it to like adversarial. They just found out kind of that if you do adversarial training, and that's actually one of my discussion points, that if you do adversarial training, the network becomes more consistent even for representations of adversarial images. So they haven't done any kind of, they didn't try to do that like with optimization or anything. It just happened to happen. And actually, that's a good point because that's one of my discussion points as well.
Is there a question?
Hey, I just want to know if, because you just modified the add consistency metric over there in the objective function, if we using this kind of adversary training model to do the classification, is this kind of classification accuracy will be kept or it will be dropped? Compared to the original model.
You say the accuracy of the network which is trained by adversarial training compared to the original. Usually it drops a little bit, but it shouldn't be huge. But usually it's like some beeps small.
I don't know whether it's worth to add this kind of components into this model to compromise the efficiency of the model to this kind of with so-called interpretability over there.
You mean so I think what you say the accuracy drops.
Yeah. I don't know whether this kind of it's worth to do it or not.
So
usually.
Yeah, the trade-off that they're making is, so since the accuracy is dropping, but if you look back at the images, the bird head neuron does not fire in the adversarial examples. So now there is some level of interpretability to that neuron. So although the accuracy might drop, you can look in at the individual neurons and come up with a justification as to why this classification was made, so you can trust your model more.
When you say neuron, the interpretability of neurons, it's actually not the input, but the hidden layers, right? Like which one actually represent. So then it's like a type of feature selection, right? So then you say, okay, so like this neuron, it has this aggregated information from this input, and then it represents like which concept, right? Is that what you mean?
Yes.
Interpretability.
If they compare like this concept with like tabular data, that's exactly the case. So it's the feature importance. Exactly.
Feature importance of this patch of pixels, you mean, right? The covariates that represent this pixels.
So like for dive, what is the importance?
You want it to be like more or less stable for a fixed label or whatever.
So we hope that this neural network decomposes the images the same way as humans do.
Actually, we hope that, and that was like the observation from like earlier papers that there is this paper saying like deep neural networks find semantically meaningful. So there's this paper, and everything came out like this, like after that one. So it just happened that we found out that the networks are really using on something that it makes sense to us. They're looking at faces. They're looking at wheels.
So it's happening all over the architectures, or depends on the specific architecture or number of layers?
Depends on the layer, right? So because your layers, the deeper you go, you have a bigger receptive field, right? So if you go towards the latest layers, are you picking me up? Okay, so I'm saying it depends on the layer of your, like how deep you're going. If you're deeper, then you have a larger receptive field. So you pick up things that are more global. You can pick things like humans. If you're a little bit closer to your input, then you may pick up faces. Go lower, you can be closer to your input than nose, then all the way to edges.
Sorry, a question regarding this, right? So representations are representation of the neurons after the filters. Like this is still at the convolutional layer, not at the hidden layer that she mentioned, right?
It could be any of those, like any neuron. So you just look at the activation of that neuron and find out where that neuron is highly activated. So it could be like the convolutional layers or even the fully connected layers. But it's more meaningful, I think, for convolutional layers because it like becomes more.
VGG16 is like, yeah, 4,000 or 4,000 hidden layers.
And as Hassan mentioned, I think there are like kind of closer to the last layers. Yeah. So even if you look at the first ones, usually are like edge detectors. But when you go further inside, deeper into the network, it gets more meaningful.
All right, let's go through the discussion.
Yeah, sure. So if you remember, one of the things that we showed in the first part of the slide, and I told you to remember that, is that the representations are different when you use different algorithms. For example, GradCam claims that they do have some results showing that the representations are consistent between the images and adversarial images. They are not, it's just a very small subsection, maybe one paragraph in that paper. So they haven't done this rigorous kind of study. But I think it's worthwhile to look at not only the saliency map, but also on other kind of interpretation algorithms to see what they see in those concepts. Are the results still valid for other methods or not? The second one is that, as I mentioned in that graph which showed the loss in epsilon 1 and epsilon 2, FGSM is not always the best case. So that would be interesting to see the results again for different algorithms. There is one bottleneck here. Other algorithms are usually very slow. They have better results, but they are very slow. FGSM is so fast, and it can be done like 500K times. So maybe using other techniques that cannot be that scalable. But it's good to have them. One very important thing that I think is kind of not good in this paper is that simplification, going from this to this. What happens is that FGSM maximizes the loss function. So it's valid for the first term, because that's what it does. But for the second one, which is looking at the distance between the feature maps, that's not what FGSM is doing. So how do you simplify this with this? These are not consistent. And actually, there are techniques which look at the feature maps, and I showed like GradCam. So there are GradCam-like kind of adversarial examples. For example, Jacobian-based saliency map attacks. Those are based on maximizing the distance between the feature maps. So I think as shown here, x star, x prime are different. They should be different, and they should be created with different adversarial attacks, which are defined for these two different loss or distance metrics values. The other thing is that we don't know if the same thing happens with any other adversarial trainings as well or not. So I think there was this question that how they found that interpretation is good for this. So it would be good to just remove, they claim that everything is improved because of adding that second part, that distance between the feature maps. So why not including some results without that and then say, okay, this is the improvement we get. Exactly. So I think that's a missing part. The other thing, which is a broader question I've always been thinking about in this area, and I have been lazy to check it, it's easy to check, is that we know that in image, the eyes of people, humans, are more sensitive to the phase of the image. And it's less sensitive to the amplitude of the image. And what we do here is to perturb the amplitude, because like the value, mostly like the value of the pixels. So
what's the phase? What's the definition?
If you take the Fourier transform and look at the amplitude and phase of the Fourier domain thing. So just take the Fourier transform of the image. It gives you the frequency domain. So and find the phase of those vectors, like the Fourier domain vectors.
So if instead of adding noise to the on the actual pixel level, you added noise on the Fourier level.
Mm-hmm. So you could repeat this doing the Fourier transfer of all the images before doing the whole thing, right?
Yeah. So basically what I'm trying to say, yes, they are not detectable by a human, but they are detectable by network. Maybe it's because something is happening in that amplitude phase kind of thing. And you know that attacking voice with, like doing these adversarial attacks on voice is harder than images. And human ears are more sensitive to the amplitude compared to the phase, which is, so in the images, the eyes are more sensitive to the phase, but the hearing system is more sensitive to amplitude. So, and it's harder to attack voice commands than images. So maybe there is a relationship here. That's just a vague hypothesis.
Through Fourier transform, then add noise to them, then inverse transform them, and then add.
Yeah, you should try it. I'm lazy enough to not doing that. Yeah, but it may work.
Oh,
That's the question I have.
Oh, okay, sorry.
I haven't done it. It's just a question. Does it work or not?
We had a comparative question about an hour ago from online. I think it's the right time to inject in there. Venkatesh asked, has the usage of optimal transportation been considered using the Branier approach, where the discriminator and the generator collaborate rather than compete with each other? This can be used during training, where the generator helps the discriminator in letting in know about the minimum delta for the purpose of distinguishability. And then in the actual run, you could have them compete against each other. If that makes sense. I haven't read papers. So I don't know. Anyone has any?
The short answer is,
like with the first time, it was like, that's confusing. It has a GANs network in it, and then you try to find out if you can get a noise to the GANs network. What is the confusion that you got? I guess you may, you should try to answer it the way that you answered it. That okay, this is adversarial network, but it's not GANs. It's another type of architecture.
Yeah. So that's the answer.
Oh, so then that means that this network architecture does not include two components, generator and discriminator,
Exactly.
only
It's
the
just-
discriminator.
Yeah.
So when you say adversarial network, so you were giving adversarial examples. The network is not adversarial.
Exactly. Yeah.
Can I ask one question? So with regard to your, there are these methods, this is comparative, so there are these methods where usually in GANs recently, where you sort of progress. So if you go to the loss function where you have two maxes, do you think it's a viable solution, and so as opposed to simplifying, like dumbing it down to that level, to keep one of them constant, train with regard to the other, and iterate and do and vice versa for the other one? Because I've seen that being used.
Yeah, I think it's a very good concept. Yeah.
So whoever is going to try that, you're welcome.
So then is
I want to
this?
say that the theta, because they just try to optimize the parameter as theta, but because the theta is in both of the objectives, probably cannot do like that because.
What the simplification, what happens is that they using that theta, they generate like adversaries. So his point, I think, is that once you do that adversary image, find that one with a fixed theta for the first one, and then the second time just keep this one. So I think it's in the lines of finding the adversaries for the two things.
So the problem is it's hard to train that because they're bivariates, right?
Yeah.
In practice, you could just have like two optimizers where you step through them in even and odd epochs, right? Or even and odd steps.
Sorry, this is univariate, by the way. It's not bivariate. With respect to theta, right?
Oh, both are with respect to theta. Right. Yeah, that's right. But
yeah, I see your point.
It is not just bivariate, it's bilinear.
It's bilinear.
And so does collaborative filter.
Collaborative filtering?
Yeah, it's also bilinear, and the SG solver, it works really well there.
Interesting.
Matrix factorization.
Yeah.
I mean, L and phi's are not linear.
So then, sorry.
Okay, so that was a good point. Could you say that louder?
So L and phi's are not necessarily linear in theta, right? It can be highly nonlinear. But anyways, I guess.
So it's non-bilinear and non-bivariate. but I want to put that out there. It's a good question. Then is it actually, because you started with it's hard to train it then. So is there any does the equation tell us anything about why it's hard?
It's just it's a highly nonlinear kind of thing. So you should find out this x star, which maximizes this loss, and then minimizes for theta. So it's I don't know, but the problem is that SGDs never work good for min-max problems. So you have to have some kind of regularization somewhere to help it to come up with an equilibrium somewhere.
I see. So it's less about the fact that you have two maxes, but the fact that you have max.
Yeah, even with one max, it's a hard problem to solve. And now it's harder because you have two maxes.
Gotcha.
Couldn't you simplify that term where instead of looking for the adversary to maximize the distance, couldn't you try to replace that with like a triplet term so that you have the distance between a sample and all of its adversaries are less than any one from a different class? Less than the difference from the feature map of a different class? So the distance from cat and cat plus adversarial noise should be less than the distance between cat and dog feature map for all adversarial samples. Right.
I don't know how to formalize it like mathematically, but
just replacing that term
So it seems related to some of these recent results on learning.
Could you speak louder?
Yeah, some of these constraints I've seen in recent results on training with verification. So you want a verification term in your loss function that actually gives you guarantee that certain things don't happen. There's a DeepMind paper recently. Learning verifiers via verified learners. I guess they actually discuss how we can build in some adversarial robustness into the algorithm like this, putting these internal conditions. Maybe, perhaps.
Is that a good paper to be presented by him?
Yes.
Are you interested?
There's a question here.
Yeah, so my question is, so the adversaries here are the minority class, right? Or they have like about the same amount as the actual pictures or not?
10 times more than this.
Based on the paper, they said that for each image they have 10 adversaries. So even they are more like dominant, actually, based on their.
So the fraudulent class actually are more than the actual data.
The perturbed images are more than the original images.
Significantly more?
10 times.
Yeah.
Okay, 10 times.
In the data set we were using, there were 10 different classes, yeah. So each image has an adversary in all of the other classes. Right? So they have the original, like the cat image, and then the cat image is its adversary into the dog class.
So then is this more like reducing the false negative problem, right?
It's reducing the
by
false
proposing this new loss function.
Yeah.
Okay.
That's the whole problem of adversary.
The way they labeled them, the artificial, it was like, they labeled it for each class.
Label what?
So they mentioned, they gave the adversarial images different labels, right? So they labeled them based on each class, like.
Yeah. So you have this original image, and then, so you can have targeted adversarial examples. You can say, I want this class to be classified as class 1, to be classified as class 2 or 3 or 4. So you can have targeted adversaries. So you can say whatever to be classified as whatever else.
My question is more like, if you have the original, data set, and then you mislabel them, what's the difference between that and then generating the...
Because if you mislabel like dog as cat, the network won't ever learn it because you're giving it false information. But what's happening here is that...
It depends, like, to the proportion of the mislabeled data.
But what is the point? Here, the point is that we have cats, and then we have cats with noise. We want the network to classify both as cats.
The idea is when you look at, so when you add that noise to the cat, it is now getting misclassified as dog. But if I showed you a human, both images, you'd think that they're the same thing. You'd think it's both a cat.
Yeah, and then...
Whereas if you mislabeled your data and I showed you the incorrectly labeled dog, you'd be like, I don't know, what is that?
Yeah, makes sense. So the other question they had is that, do you have any examples of the images that, the adversarial images that they created?
Not in the paper. The only thing, the images they have is this one this one, yeah. But they are not, I assume they are not very, like, visually different. Yeah, but no, they don't have, like, large compared to image.
Any other? Oh, sorry. Did you want to say?
I don't know.
Any other questions? Oh, you were. Any other points?
Any comments or? Because, no.
Just
sorry.
Probably something unrelated. Is there a paper that seek to confine the perturbation to only the receptive field and nowhere else.
Yes, that JSMA, the Jacobian-based saliency map attack does that. So what it does is that it finds the saliency map, which is like the receptive field for that thing, and tries to only perturb like points in those regions. Yes.
And its performance is not as good as this one.
It is actually better.
Oh.
Yeah, it is. And sometimes the image that, the thing is that sometimes the images they come up with, like the adversary images, they are visually detectable. That's the problem with that.
That's a good thing, right?
It is a good thing, but it's a little bit not consistent with the goal of adversaries.
Yeah, but it also confuses human.
Yeah.
So that means, you know, it's like one step closer.
Yeah, maybe.
I can't think of some other application of that Jacobian salient attack. Could probably just paint it on your face.
True. Yeah.
So, clarification question on that, and then we'll close with that. So you're perturbing not the feature maps per se, but the Jacobian of the feature maps. That's what I understand. Is that?
Yeah. So what it does is that it just looks at the gradient of output versus input and sees, look, these are the important pixels in the image, and it adds the noise, kind of tries to perturb those kind of pixels.
But I thought you said they look at the feature map as opposed to the pixels now.
And it's before the gradient is from the feature map versus the input.
I see.
So it's like before the
loss.
The loss.
But I see. Okay, I see. Interesting. We had a question over there.
Yeah, just a very basic question. So suppose you take all these observed examples, you know, say the catting is obviously observed pictures, and then you, with the label catting, put them all in the training set, and then you train the same model with it. It's very simple. How would that compare to this method? Like what would happen to these consistency of the neurons and so on?
Sorry, just to repeat the question, if I understood correctly. So you have like a bunch of images, you find the adversaries and put them together and train it. That's what
you model, and then you create all these observed examples, and then instead of doing what you just described, instead you just put it back in the training, like you just train the model again, but on those new images as well, and train it like with the correct label. So perturb it, but you still say it's still a cat, even though it's classified as a dog. Mm-hmm. You train it again.
That's actually. That's what they do. This optimization is just a like math kind of formalization of that.
Without the second term, right?
Yeah, the second.
Without the second term.
Yeah, without this. Actually, they do the same thing.
What you're referring to is this or the other one?
Yeah, actually, they do the same. Like they find like the adversaries, they put it back to train it against it as well with the correct.
Give the signal of the.
Exactly, and actually, and that method. Goodfellows, there is a paper from Goodfellow, that ensemble paper I showed multiple times. They showed that that technique works better than this because it's better. That's something very interesting about adversaries. The less you know about the network, the better the attack would be. The less you know about the network, the better the attack would be. It's like, and it's shown in that paper that when you have adversaries which are generated by other techniques and use it against the network you want, it works better than doing this. Find the adversaries with that network and train it against it. So yes, the thing you say is sometimes even better. Or even the black box attack, which is you have the network, you assume that you don't know anything about it, you feed it with a bunch of inputs, you find the outputs and train another network on top of this input and output and try to find that boundaries and then create adversaries with that, then attack the original network. The training you do this way is more robust than training the network versus itself.
So a surrogate sort of.
Exactly.
It's more effective.
Yeah, it is. And that's why they say it's better to know like less about the network. And I think something about those kind of overfitting to some regions, it's easier to, because the network tends to locally overtrain, finds boundaries which are nonlinear, very nonlinear locally. But when you have a surrogate model, those nonlinearities are kind of smoothed out. So you have better adversarial examples now, which if you use for training, it becomes like more robust. The network becomes more robust. Did that make sense?
All right. Any other comments or questions?
Just maybe last one.
Yeah, absolutely.
Do you know any?
You're supposed to help me.
You're supposed to.
Good job, by the way.
Do you know any empirical study that looks at the relationship between robustness to adversarial attacks and basically generalization of algorithms? So the question for me is, what's your view on robustness to these kind of on robustness to synthetic examples, and again model overfitting, or because
so again, this paper that I mentioned again from Wagner's, that one has a very good discussion on this, but it's mostly like it's like numeric simulation-based kind of discussion. It's not like mathematic kind of discussion, and I have no idea how they are really.
Sir, could you repeat the question?
So I guess if somebody sees this stuff for the first time, they might think, okay, this model perhaps is overfitting. The model just latches on everything it can, and then okay, so you change some stuff, very minimally, and then the prediction changes. So my question is whether there is actually deeper reason for existence of these kind of examples. And if a model turns out to be, for example, not overfitting, but a lot of these state-of-the-art examples show that they are not overfitting, they actually have very good generalization capacity. So my question was, what's the relationship between not overfitting or exhibiting good generalization and being robust to adversaries?
If it's overfitting, then theoretically you can mix it with random noise, not just adversarial noise.
Right. Yeah, going one way is easy. Yeah. So.
Yeah.
Interesting question. Any other comments or questions? All right, let us thank the speaker for the great talk.